Hello, everybody, and welcome to my presentation of this work entitled Risk Targeted Hazard Maps for Spain. This study has been done at University of Alicante by collaboration of my three other colleagues, Professor Sergio Molina, Professor Juanjo Galeana, and Dr. Noelia Aguiar. In this presentation, first, I want to talk about the importance of the problem. Then we will talk about the seismic hazard model, which we were considered in this study. After that, we will briefly explain the computing the risk-targeted ground motions. Later on, we follow the presentation regarding the estimation of input parameters. And at the end, we will demonstrate some results and discussions obtained through this work. Many studies have demonstrated that the design of structures in a region through the uniform hazard principle does not guarantee a uniform collapse risk. Even in regions with similar peak ground accelerations corresponding to the same mean return period, the seismic risk in terms of collapse probability will be significantly different. These inconsistencies are due to the different shapes of the hazard curve for different regions and uncertainties in the yielding or collapse capacity of structures. Hence, a structure can collapse due to different ground motion than what it was designed for. So it would be more consistent to use a uniform risk assumption instead of using uniform hazard. While some research has been carried out on the importance and influence of input parameters in risk analysis, only a few studies have attempted to consider the distribution of these parameters, considering their variability through this probability framework in risk targeting analysis. In this study, we developed new risk targeted seismic design maps for Spain, contemplating two different damage states, means collapse and yielding. Also, this research aims to determine whether there would be a significant variation in the current design's PGA values while considering the uniform risk assumption using an updated seismic hazard in peninsular Spain and the employment of variability in model parameters of fragility curves. It should be noted that these maps were obtained for the design of new structures using seismic design codes. And moreover, we assume that the most common buildings in Spain are reinforced concrete moment frame buildings. Let's start talking about the seismic hazard model considered in this work. We can say that Spain is a country of low to moderate seismic hazard when compared to other European countries, such as Italy or Greece. However, the country has suffered several damaging earthquakes in the past, as you can see here in this slide. And therefore, the first National Seismic Building Design Code using a probabilistic seismic hazard map was approved in 1994. Later, the code's seismic hazard map was updated after the damaging earthquakes that occurred in the southeast of Spain. The results were computed as PGA for 4 annual probabilities of exceedance. However, as more annual probabilities of exceedance are needed to better define the slope of the hazard curve, we have computed an updated seismic hazard map obtaining 20 values of annual probabilities of exceedance for corresponding PGAs. You have to mention that the probabilistic seismic hazard assessment was obtained in terms of PGA for rock side conditions. Since the shape of the hazard curve is one of the important parameters in risk-targeted analysis, we estimated the distribution of local hazard curve slopes. At first glance, this may be perceived that at national level, not much variation can be expected in risk-targeted design ground motions due to the almost similar slope of the hazard curves. But here, a few important points should be made. For example, a simple look at the right figure in this slide, we can see that no curves can be approximated by line. Hence, computing the slope of the hazard curve is a biased process. Moreover, a small variation in the slope can cause a large difference in the risk of collapse. Nevertheless, the risk targeted design ground motions depend not only on the shape of the hazard curve, but also on the input parameters of this related fragility curve and the acceptable structural performance. As we said before, in this study, risk-targeted maps were developed based on an updated seismic hazard map of Spain. The annual risk was calculated by using the famous convolution product between seismic hazard and fragility functions. But the integration in this equation does not have a closed form solution. Therefore, an iterative process is required to calculate risk-targeted design ground motions. It means that first we have to define the annual acceptable probability of exceeding a damage state as a target value. Therefore, it's necessary to define an acceptable level of seismic performance. Different suggestions have been proposed in other studies and seismic codes, but in this study to calculate the acceptable threshold for the annual risk of exceeding the damage state, a framework similar to that of Loco et al. 2007 was followed. Two structural performances were considered, namely collapse and yielding. So now we can say in risk-targeted analysis, we have to estimate the parameters corresponding to, let's say, the conditional probability of collapse or to the conditional probability of exceeding yield damage state at the design ground motion, the logarithmic standard deviation of PGA, beta, and the acceptable annual probability of exceeding a damage state. Regarding the collapse as a damage state, to consider the variability of the relevant parameters for developing the fragility curves, a multivariate normal distribution of input parameters was employed. Regarding the yield damage state, since previous studies have indicated that there is a little variation between the relevant input parameters of fragility curves, the values proposed by Rich et al. 2014 were considered to perform the risk analysis. So the target probability of collapse was estimated through three different assumptions. In the first method, the fixed values were assumed. These values were calculated by obtaining an average over all the sample beta and probability of collapse for a given ground motion. Once again, to consider all uncertainties due to the building to building variability, all the possible values of beta and probability of collapse for a given ground motion were extracted from the multivariate normal distribution. And in the third option, for every site, the corresponding values of beta and probability of collapse for a given ground motion were estimated according to the Crowley fragility curves. After the comparison of the obtained results through these three assumptions, the value of the annual target risk of collapse and the acceptable annual risk of yield have been estimated, as can be seen in this slide. In the next step, as mentioned before, assuming average values of beta and probability of collapse for a given ground motion, and then considering the building and site-specific fragility curves for each of the 5,249 sites, the risk-targeted ground motion maps are presented. In this slide, we can see the distribution of risk-targeted design ground motions and the distribution of risk coefficients for peninsular Spain. Here, the Crowley et al. Fragility curves has been used to develop the risk-targeted maps. And this slide displays the risk coefficient distribution, assuming the yielding damage state using the values proposed by Ulrich et al. 2014 for the fragility curves. On the right side, the corresponding uniform hazard PGA with a mean return period of 95 years of peninsular Spain can be seen. After the comparison of the obtained results, we can highlight some remarks here. The structural design based on ground motion for a given return period results in an annual probability of exceeding a damage state that varies from one area to another. Annual risk of collapse depends not only on the ground motion design, but also on the shape of the hazard curves in those areas. Of course, the effect of uncertainty on the capacity of structures should not be dismissed. A fixed value for input parameters of fragility curves could lead to an overestimation or underestimation of the collapse risk in some low or high hazard areas. And from the results can be said that the more the design ground motion, the higher the risk of collapse. Therefore, if the mid-range of collapse risk as a target risk is selected, this leads to a decrease in design PGAs in low hazard areas. For collapse as a damage state, the most significant variation in the design ground motion is related to high seismicity areas in Spain, and the modification of design ground motions for low and moderate hazard risk regions corresponding to the yield state is more significant than for the collapse state. It's strongly recommended to use fragility models according to the specific typology and corresponding with the design ground motion of that region. And also we strongly recommend to download our paper and look for more conclusion and discussions, since here in this presentation, we couldn't mention everything because of time. At the end, thank you for your attention.